Hey, everyone. Thank you very much for coming to our talk. My name is Yaniv. With me here is Ben. We're both security researchers, and we work at Checkpoint Software Technologies. And we're here today to talk to you about cryptographic failures. And the thing is, if you did anything to do with malware for the past few years, then you probably know that cryptography is something that malware really started using a lot during the past few years, right? So more malware is using cryptography, and more malware is using better cryptography. And this sometimes can put malware researchers and malware analysts in some kind of a sticky position where they are expected to show abilities that are usually reserved to mathematic PhDs or crypto analysts, right? You are now expected to break this crypto system, and sometimes this task can look a bit big, and you don't really know how to do it. So we prepared this presentation in order to show you that this is actually rarely the case, because most times the bugs are not actually in cryptography, but the bugs are in the man implementing cryptography, right? And in order to do that, we've picked a few examples that we've researched during the past few years, and hopefully you can have some takeaways on the methods and techniques you could use in order to fight against this cryptography and maybe turn the tables on the malware authors and use this cryptography against them. Just a short disclaimer before we begin. All the examples you're going to see here have either already been fixed or published before. And that is because we really believe that, sometimes we see individual researchers or even AV companies or security companies just posting, hey, we found this crypto bug in this malware, and it's a great blog post, and it also gets great PR, but we believe it's the wrong thing to do, because all you're actually doing is giving the malware authors the exact information they need in order to go and fix their malware, get up and get a new version out there, and now your blog post is irrelevant, and the entire industry just lost its edge on this malware. So there's nothing new. We disclose all the new findings we have privately with the community, and the examples themselves actually are not really important, at least in my opinion. What is important is the takeaways from these examples. And now, without further ado, I will let Ben present the first few examples.
Okay, thank you, Yaniv. Okay, so the first category of crypto failure that we're going to talk about is voodoo programming. Now, voodoo programming is programming that stems from a warm, fuzzy feeling in your gut that the code you're writing right now kind of seems like it could be the right idea in theory. So, some crypto failures completely wreck crypto systems. And then other crypto failures don't do that much damage. They mainly give us a window into the paranoid, delusional soul of a malware developer, and the way that fundamentally they have no idea what they are doing. So, let's talk about Zeus. It's the granddaddy of all banking trojans. It infected millions of machines and caused tens of millions of dollars in damages, but we're not here to talk about that today. We're here to talk about the way that Zeus encrypts its outgoing traffic. To encrypt its outgoing traffic, it uses something called RC4. Now, RC4 is a stream cipher invented during the 80s by Ron Rivest, and it's really popular to use in malware for two reasons. First of all, RC4 is really easy to implement. If you look at the image up there in the slide, half the RC4 logic is already in there. And the second reason RC4 is so popular to use in malware is that it's good enough. I mean, yes, we may have heard about attacks on RC4 and so on, but for such a use case of encrypting outgoing traffic of malware, RC4 should do. But, the Zeus guys did not agree, so they decided to introduce their own redesign from the ground up of RC4 that we like to call Zark4. Now, if you look at Zark4 and compare it against RC4, you'll see that the actual difference is just those last two lines. What they do is that once you have the RC4 ciphertext, those last two lines, take each byte of the resulting ciphertext and XOR it with the next byte to create a new and improved ciphertext. Now, by now, I've told this story to many people, and what they all had in common was their complete lack of a reaction to that last part, which is a pity, because guys, if you take a crypto system, and to the end of that crypto system, you append a constant linear transformation, you have added zero security to that crypto system. None. It's completely useless. It's like relaying your ciphertext in pig Latin. Now, out there, you know, it's not that just the Zeus guys that do this kind of thing. Out there, there is a veritable sea of malware doing all of those changes and introducing all of those tweaks to crypto that's been known to work. So we're left with only one question that's natural to ask, which is, why? Why do the Zeus guys do this? Now, we can't read the minds of malware developers, but we have a working theory, so let's put ourselves in their shoes for a moment and see the world from their paranoid point of view. They believe that somewhere out there, there's this shady guy who wakes up every morning and says to himself, today I'm going to read me some Zeus traffic. And this guy has access to a magic box, which is capable of staring RC4 ciphertext straight in the face and decrypting it just like that, without having the key. Now, I am not capable of such a feat, and I am going to guess that nobody in this room is capable of such a feat either, but this guy can do it. And the Zeus guys cannot bear to live with this kind of threat. So, in their desperation, they resort to the only trick they can think of resorting to, which is, in this case, a Jedi mind trick. Which means that they take their hand, extend it forward, and say, Mr. Agent, this is not the algorithm you're looking for, because you see, your magic box works on RC4, and we're using Zark4. It's completely different. It has this linear transformation at the end. And what they expect to happen is for this agent guy to just, go stand in the corner and cry. Now, actually what would happen if we assume that such a guy with such a capability even exists at all, is that he's going to take 5 minutes to figure out what they did, right? Look at some reverse Zeus samples, look at some traffic captures, and put 2 and 2 together. And figure out what they did, and take the Zark4 ciphertext, apply the inverse linear transformation to it, and then run his magic box on it, and now he has the plaintext, and we're back at square one. Actually, we're not quite back at square one, because earlier this guy had a problem, right? He woke up every morning, and he wanted to look at Zeus traffic, and he had to fish it out from the sea of other RC4 encrypted traffic. But now Zeus is using its own encryption scheme that only Zeus uses, which is Zark4, and we just established that this guy can decrypt Zark4. So all he has to do is easy peasily take his Zark4 decryptor and search the web for traffic that can be decrypted using this decryptor. And by lunch, he's going to have all the Zeus traffic. So even if we adopt the assumptions that the Zeus guys started here working with, we end up with the conclusion that the Zeus guys may have tried to disguise their traffic, but they ended up just drawing more attention to it. Okay, so next example that we're going to talk about is Linux encoder. Linux encoder is the first ransomware reported that was targeted at the Linux operating system, discovered around late 2015, and it mainly propagates via a vulnerability that was discovered at Checkpoint, so here's a link in case you care about that. Now, on the face of it, Linux encoder knows how to do encryption. It uses the AES algorithm. It uses it in the CBC mode of operation, so you cannot see the penguin. And it uses third-party open-source crypto libraries, which means that the chances for strange homebrew crypto bugs are lowered compared to if they didn't. Now, much like other ransomware of its kind, when a Linux encoder runs across a victim file, it generates a session key in order to perform the encryption. And in order to randomly generate a session key, you need access to a source of randomness. Now, if you're on Linux and you need to randomly generate a number, usually you would use dev-random or dev-urandom. But those guys came into it in a very Windows frame of mind, so they decided to use the current timestamp as a random seed to generate a random number. Now, even if you're on Windows, that's not the best way to do it, but those guys said to themselves, what the hell, it's going to work, right? Why spend any more time on it? And indeed, if you're going to look at the Linux encoder executable, the very first thing it does is pull a random value based on the current timestamp as of the execution time, and then that random value is used to later pseudo-randomly generate all the other random values, including all the other session keys, everything. So let's go over what we just did. We used the current timestamp to generate a session key. We used the session key to encrypt the victim file. We wrote the victim file to disk. So where's the catch? Let's think about that for a moment. We just created a new file with new and encrypted contents, and another new thing this new file has is a new timestamp. Do you see where this is going? Okay, do you see it now? right? What's going to happen? The victim now has access to the newly created encrypted file, which has a timestamp, which is kind of like the old timestamp, which can be used to generate the session key, which can be used to decrypt the file. This is kind of like the villain of the movie Taken, calling Liam Neeson and saying to him, I have your daughter. I'll never tell you where she is, but you should know that 2 seconds ago she was at the hotel lobby. That's, now, of course, the community could not just let this excellent design choice pass by without comment. I believe the credit is due to the guys at Bitdefender for spotting this gem. Now, this is completely useless advice, courtesy the Grok. I mean, running the hash function on the timer is going to add 0 security, but you know, the Linux encoder guys, they took one look at this and with wide eyes, they said to themselves, yes, that's what we need in order to improve our ransomware, more hashing. And soon enough, a new and improved version of Linux encoder came out, which generates session keys by taking the current timestamp and invoking a hash function on it 8 times in succession. 8 times. Now, as we all know, that's 8 times as secure as using a hash function just once. Now, to be completely fair to the Linux encoder guys, they did fix the original problem. They made sure that the encrypted file timestamps will have the same timestamps as the victim file, so the attack I described earlier was no longer viable. But there was a slight issue left, though. They forgot to tell Polar SSL what hashing function to use. So as a result, all 8 calls to the hashing logic did not actually do anything. And what happened is that the seed that was appended to the end of each file for the purposes of verification was identical to the key that you needed to use in order to decrypt the file. So basically what this ransomware did was encrypt all the victim files and to the end of each file append the key that you could use in order to decrypt the file. Right? But you know, except for this one act of kindness, the ransomware now works perfectly. So what are our takeaways from those 2 examples? First of all, if your encryption is not broken, don't fix it. Second of all, if you're up against time-based crypto, which means cryptography that uses the current timestamp in order to generate random keys and so on, you should follow the timestamps because you might find something interesting. And third of all, and most importantly, don't listen to the Grok because he's probably trying to troll you. Now, the next category that we're going to talk about is what we like to call the copy and paste problem. Now, I'm sure nobody in this room has ever copied and pasted code, but I hear it's something common that people sometimes do. Now, one example of people doing it is the crypto defense ransomware, which first appeared around 2014, and it's a clone of CryptoWall, which is a clone of CryptoLocker. You can see up there the ransom nodes for CryptoWall and Crypto Defense. They're nearly identical. I can barely tell the difference. So how does crypto defense perform encryption? Well, on the face of it, pretty well. It uses public key encryption. It uses the RSA algorithm. And what happens is that when an infected machine gets hit, it first generates a private key and a public key. The public key is used to encrypt the files on the victim system. The private key gets sent over to the CNC server, and now only the CNC server can decrypt the files. Now, actually, if you're writing ransomware, not that you should, but if you are, what you should do is generate the keys on the server side. So we rate this ransomware design 2 stars out of 5. But actually, I've seen ransomware earn good money that I would have rated 0 stars out of 5. That's not really a big issue. It's not the best possible design that we are looking at here, but it's a working design. And in order to make this working design a reality, the crypto defense guys needed access to a working implementation of RSA. Now, one way to do it is to use the Windows native cryptographic API directly. And another way is to use a third-party wrapper library for it, but they decided to use the native API directly, maybe because it's less bulky, maybe because it draws less attention, maybe just because all the cool kids are doing it. But anyway, if you're going to use the Windows native crypto API to encrypt stuff, you're going to have to be familiar with those 3 functions. The first of which is crypt acquire context, because you know, this is Windows, you can't do anything without acquiring a context first. Now, in order to properly invoke the crypt acquire context function, we're going to have to do one of my personal favorite things in the whole wide world and look at the MSDN documentation. Now, all of this is fascinating stuff, but excuse me if I skim right over to the function prototype. And now, if we look at the parameters, it's pretty easy to figure out what should go in the first 4 parameters, but the last parameter is the flags parameter. Okay, now, hands up, everybody here knows to tell me point blank what should go in the flags parameter here. Okay, I have no idea either, so I scroll down to the documentation for the flags parameter. Actually, this wall of text is the documentation for just one flag. And skimming it quickly, I discover several things. First of all, the flags variable should usually be set to 0. But on the other hand, the crypt verify context flag should usually be set. So in summary, this variable should usually be set both to 0 and to not 0. Now, I'm a reverse engineer and not a quantum physicist, so I really don't know what to do with this information. And by now, I'm dazed and confused, so I scroll down some more, and by golly, I hit the jackpot. It's a fully formed call to crypt acquire context, right there in the MSDN documentation. And what is the flags variable? It's 0. It's just 0. So my confusion is over. And the same goes for the crypto defense guys. Why? Because they went through the exact same mental process that I just outlined. How do we know this? Because if you look at the crypto defense executable, this same exact code appears there verbatim, word for word. So, problem solved, right? I mean, they copy-pasted code and all of that, but I'm starting to get second thoughts about all of this documentation that we skimmed. So let's roll back for a moment and look at the documentation for the crypt verify context flag. Now, what does this say? When this flag is set, temporary public-private key pairs can be created, but they are not persisted. Now, we did not set the flag, so let us take the contrapositive of this statement. When this flag is not set, temporary public-private key pairs can be created, and they are persisted. In plain English, what this means is that the super secret key that we're keeping away from the victim and asking money for it, a copy of it is kept in the persistent local key storage somewhere under the user's application data folder. Right? Not exactly what the crypto defense guys must have had in mind. Okay, so what are our takeaways from this example? First of all, the less intuitive the API, it might be more difficult to reverse engineer, but it's also more difficult to work with. So it might be more difficult to actually dig down, but the chances of finding some juicy mistake go up. And second of all, if you get hit by ransomware, go check your local key store, because who knows, this might be your lucky day after all. So without even further ado, I'm going to pass this thing right back on to Yaniv.
Thanks, Ben. Okay, so to our next category, which is reinventing the square wheel. I guess this needs no further explanation, kind of self-explanatory, right? So let's jump right ahead to the next example, which is another ransomware. They are not all ransomware, don't worry. So this one is called Petya. Most of you probably heard of it. And that's because it was pretty famous, like in the beginning of 2016, I think. And that was actually the first ransomware to ever encrypt the MBR. Right? So MBR stands for Master Boot Record, and that means that this specific ransomware did not only take your files as hostage, but it actually took your entire operating system as hostage, right? So after you've been infected and rebooted the machine, you are presented with this very scary red skull ransom note thing demanding you to pay the money, obviously on another computer, because your computer is completely unusable now. And that's practically it. Now, I always like to say that when you are reading code or reading assembly or researching something, that you get kind of an intimate knowledge of the guys who wrote this code, right? And we had the same feeling here, and we tried to think, who are those guys behind the Petya ransomware? Who are they? And we gave this bit of thought, I think maybe too much thought, and then it kind of finally hit us. And now we know who those guys are. You see, those guys are simply malware hipsters. That's what they are. They like doing stuff in the unusual way, right? So they did it all over the place. I mean, look at the MBR encryption thing. We can argue whether or not this was a good choice, right? It might have been good, might have been bad. But what we can't argue about is that this thing, it was innovative. It was the first time to ever been seen, right? And this goes on throughout the code, and more specifically, this is also true for the choice of encryption algorithm for this, right? I mean, I can imagine those Petya guys sitting in a table and saying, we're not going to use any of this common encryption algorithm, any of this capitalistic encryption algorithms. We're going to use something of our own, something unique, something piquant, right? And since piquant was where they were aiming for, they had only one logical choice for encryption algorithm, which is the Salsa 20 key stream. So if you're not familiar with it, it's okay. It's kind of a hipsterish encryption algorithm. But all you need to know about it, that this is a stream cipher. So that means that basically it needs to produce a key stream, then this key stream will be XORed with the plain text, producing the ciphertext, and the same goes backwards and so on and so forth. Now, in order to produce this key stream, we have this struct here, right? And it has some variables to it. Some are constant variables, like the sigma, which is just a string expand 32 byte k. You have an IV. You have something called a 64-bit stream position, which just marks your position in the current key stream generation. And then most importantly, we have two chunks of 16 bytes that contain the password, right? Now, once we have this struct, we only need to pass it through this very nice mathematical diagram, which is actually pretty easy. And if you're wondering, it's used something called, I think, add rotate XOR PRNG or something like that. It's actually pretty easy. And then the output of this thing is just a key stream. That's pretty much it. And now we are faced with a problem. With a very difficult problem, actually, a problem that humanity has faced for many years, and it's still unsolved. And I'm, of course, referring to the problem that how do you know how spicy your salsa is? I mean, how do you do that? So we like to tackle these very hard problems, and so we gave some of our best engineers to try and find a solution for this thing. And they sat on these days and nights, and we are now proud to present to you, for the very first time ever, our salsa-o-meter, right? So this thermometer here can sense exactly how spicy each salsa is, including, of course, our salsa 20 implementation. And as you can see at the moment, it's like the hottest pepper in the world, right? Something you wouldn't want to go near without any chemical protections or stuff like that. And that's nice, but let's see how the Petya authors helped us reduce this spiciness level, right? So, salsa failure number 1. I told you about the 64-bit stream position, right? The Petya authors thought it was a good idea to store this value in a uint32 for some reason. I don't know why, but this, of course, forces the 4 high bytes to be constant zeros and completely irrelevant to the entire key stream generation process. And our salsa-o-meter senses that and says that this is no longer this very, very hot pepper, but it's still a pretty hot pepper, I guess, because it's not such a big fuck-up, but it is a fuck-up. And then the Petya authors, of course, don't give up, and they produce salsa failure number 2. Now, as I said before, this is a add rotate XOR PRNG, and the rotate left is actually one of the main functions used everywhere along this key stream generation thing. And what you see in the blue box here is simply the rotate left implementation taken from C standard libraries, right? And the red box is the Petya implementation. And now, another thing I didn't mention before, if you don't know, the MBR is based on 16-bit architecture, while Petya was originally designed for 32-bit, right? So these guys had to shift their arguments from 32-bit to 16 bits, which is exactly what they did, and did it quite well. However, they very conveniently, for us, forgot to do the same for the constant values. So they kept the 32 value there, and what you have in the red box there is absolutely not rotate left. I don't know what it is. Maybe it's something more similar to shift left, not even that. However, this is a very major fuck-up, and our salsa-o-meter senses that and says this is no longer this red hot pepper, but now it's some kind of greenish, still hotish pepper, you know, still impractical to break this, but this is absolutely not salsa 20 anymore. And luckily for us, the Petya guys just don't give up, and they produce salsa failure number 3. What you see here is the main function. We called it the S20 hash function. This is the core function responsible of producing the key stream from the struct you've seen before, right? And there's a very, very major fuck-up in there. Can anybody maybe spot it? Okay, let me give you a clue. It's here. Can you spot it? No? Well, it's very simple. You see, the blue, of course, is the right implementation. And what it does is just process 4 bytes at a time, and then jumps ahead 4 bytes to the next 4 bytes in order to, produce the keystream. That's it. Now, again, you have the shift from 32-bit to 16 bits, and what these guys did is process 2 bytes at a time, and then jump ahead 4 bytes. Very nice, Petya guys. So what does this mean? This, of course, means that every other 2 byte will be completely irrelevant now to the entire keystream generation process. So with this single fuck-up, they just reduce the complexity by half. You see, by just not changing a constant value. Very nice, very nice. But again, our salsa ometer says that now this is no longer a pepper at all, but it's some kind of a Tabasco sauce, maybe. But still the hot kind of Tabasco sauce. And why am I saying the hot kind of Tabasco sauce, not the normal one? Well, because you see, usually what we want to do is to brute force this thing, right? And if we want to brute force this thing, then think about it. First of all, let's get rid of all the unrelated bytes because they are not used. And now the bytes we are left with, some of them, if you remember, are constant values. And constant values don't really interest us if we want to brute force, so let's get rid of them also. And now we are only left with the password bytes, right? And if you can count those bytes, then you see that we are still left with 16 bytes. Now, 16 bytes is very, very far from the complexity we started with, but it's still pretty impractical to brute force 16 bytes, right? It is. So, luckily for us, the Petya guys introduced this nice function. We call that key expand. I have absolutely no idea why it's here. It's not even part of the Salsa 20 implementation. It has nothing to do with it. And what it does is that it's used to represent each password character by 2 bytes. It's not Unicode. It's just some kind of strange encoding. I have no idea why it's used, why is it even there. But practically, what this does is, for us at least, instead of brute forcing 16 bytes, now we only have to brute force 8 bytes. Thanks to this function. Thank you, Petya guys. And not only it's 8 password characters that we have to brute force, but if you remember that the user actually has to enter this password through his keyboard because he has no other option, right? Then it's not only 8 characters, it's 8 printable characters, which is completely insane. At this point, our salsa meter suffered from a sudden crash. Our engineers are still working to debugging this problem. We don't know what's the problem, but the current estimation that this is no longer salsa, but it's some kind of a cucumber salad or something. And of course, decryptor was introduced after this was found, and Petya made a new version without these bugs. So, takeaways. First of all, arguments and types, they are kind of important. So, take a look at them. And the other thing is that whenever a programmer needs to shift from one architecture to another, like from 64 to 32, from 32 to 16, then you might find bugs. And if you will find them, you will probably find them in the argument types or in the constant values. At least that would be the first place I would go look for them. So if you have this situation, go look there. And now for our last example, which is not a ransomware. It's the nuclear exploit kit. Some of you might have heard of it. It's been very active between 2011 and 2016, and actually its operation completely ceased right after we published our very extended report on it. So you can, if you feel like reading it, these are the links. And now, exploit kits, we had a presentation about it yesterday here. It was very nice, and it showed a very, very complex ecosystem. Right? It's very complex. It's too complex for me. So we're not really interested in this entire ecosystem. But the thing is that it's very complex for a very good reason. These guys, everybody is trying to catch them, and they have to keep their system as complex as possible. They do everything they can in order to prevent from being caught, right? But we're not interested in all that, as I said. We're only interested in the, say, abstraction of communication between the victim and the nuclear panel, right? So what happens here? Basically, the victim sends an HTTP request. This request somehow gets to the nuclear panel, and then the nuclear panel serves the victim back with an obfuscated payload, right? With an obfuscated exploit. And then in order to de-obfuscate this exploit, those two, the nuclear panel and the victim, needs to share a key, right? And the way they decided to do that is using Diffie-Hellman key exchange, which is pretty smart. You must admit. I mean, I was pretty impressed by that. So just a bit about Diffie-Hellman. If you don't know, I'm not going to teach you about Diffie-Hellman. However, you have Alice and you have Bob, and you have an unsecured channel between them, and those two guys need to share a key between them, right? So they do something that looks like this. This is Diffie-Hellman. And at the end of this process, you have a shared key, and nobody in the middle sniffing the communication can know this key. Only Alice and Bob knows it, right? And then this could be very, very elegantly represented by this mathematical formula, right? And this formula has to be calculated on the server side, and that's how you do Diffie-Hellman. That's it. Now let's see how nuclear guys have decided to implement this. So this is the actual implementation in PHP taken from the nuclear exploit kit. What you see here is exactly the calculation of the formula you've just seen before. That's it, right? And if you'll take a look, there's a function there. I don't know if you can see it. It's called getGMP. And this function is pretty easy. All it does is just take the parameter passed to it, the argument passed to it, and base64 decodes it and return the decoded value back to the main function. That's it. Now, what you see here is the actual communication. It's JSON parsed, being sent from the victim to the nuclear panel. I wonder if anybody can spot the problem here. No. Yeah, it's kind of hard to spot, but the thing is that these parameters, they are not base64 encoded at all. They're just X values. So, oopsie. But what does this actually mean for our implementation? We'll take a look at that. So, the getGMP function you just saw before receives non-base64 encoded value, right? So when the base64 decode function gets this value, what it returns is false, right? And false is just 0. So this thing returns a 0, right? And let's take a look at the main function now. So you have the GNP parameters, which receives a 0, making this a 0, and then the A parameter receiving a 0, making this a 0. So it's 0 to the power of B modulo 0, which just so happens to be the exact equivalent of the entire efficiency of this algorithm, which is, you guessed it, 0. So a lot of code for nothing. And well, that's basically it. I just want to finish with one quote from us. If you consider cryptography to be a magic black box, then either you don't understand cryptography or it doesn't understand you. That's some thanks and credits for other guys doing research on the same things and some jokes that we took from other researchers. And that's basically it. Thank you very much.
Any questions?
Hi, thanks. What about actors sharing their bad tricks between each other?
Can you repeat?
What about actors sharing like their tricks between each other? And you know, you find it across. I think Joanne Calvé has been presenting in 2012 on that. Did you spot like people sharing this broken stuff between different families?
The actors, you mean?
Yeah, the kind
Look,
of
I believe the Diffie-Hellman trick was originally implemented in Angular, I think, or yeah, some other exploit kit. So they are sharing that, or they are copying that. I don't know, but there's nothing we could do to stop
broken
them.
implementations, and you know.
What?
Like this kind of broken implementation, like adding this linear kind of stuff at the end. And, you know, are they copying each other? Are they sharing the code between different...
You mean are they copying the fuck-ups?
Yeah.
Yeah, usually you get this kind of problem because people, you know, they improvise and they try to do it themselves instead of trying to copy a working solution. That's how you get there in the first place, usually.
It might happen. We haven't seen anything like that. I will be very happy to find something like that.
All right, thanks.
Anyone else? Thank you.